later how we shared the file, Ronan? So, sorry, 1 second. You seem to be able to record it. That'd be absolutely fantastic. Yep, so I will make Ronan, give me just one thing, because in this way we can then actually record it, which would be marvelous.
Somebody already is recording, so I don't know who that is.
Okay, so apparently now we have
I pressed the button. So
oh, great.
Fantastic. Thanks. Okay, so Miranda, thanks very much for joining us for this first QFT and Geometry Seminar on three manifolds, log VOAs, and quantum modular forms. So please.
Yeah, thanks a lot. Thank you very much for the kind invitation. So I'll just start my talk. And this I'll be talking about like one of the things that I've been doing in the past few years. And the starting point of this work is the so-called Z-hat invariant. You can call it the homological blocks, the Q-series invariants, or sometimes, you know, in the physical context, you can call it the vertex partition function, half index, or blah, 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 just to make sure that we know what we're talking about that. But I'm just going to call it Z-hat invariant. Okay, so what is it? It is a topological invariant for three manifolds, in particular for closed three manifolds. It's first defined physically in terms of M-theory compactification in 2016, and afterwards it was given a mathematical definition for a certain class of three manifolds, and later it was also defined for knot complements. Okay. So given what it is, it's naturally related to two topics. And the first is, of course, three manifold topology. And in particular, we will think about it conveniently as a generalization of the Witten-Resticking to Wright invariants, or Chern-Simons invariants of three manifolds. And because it's also defined for knot complement, so it also has something to do with the invariance of knots, of course. And in particular, I mean, knot cover correspondence will play a convenient role here. And then the other, from physical perspective, what this invariant is doing is counting some supersymmetric states naturally. But my work is about something else, really. What I really like in research is to connect things to other things. And in particular, these two things are, you know, something that I like personally. So one thing is quantum modular forms, which is a kind of a generalization of modular forms. And you might heard people talking about, or me talking about Mach modular form. It can be considered as a generalization of Mach modular form if you want. And the other is vertex operator algebra. So the point of this work is to establish the connections between Z-hat invariants and these objects, and to understand them as much as possible. Oh yeah, and I have to say that because the computer is doing really weird today, and the Google Drive is also doing very weird, so actually I lost the recent versions of this talk. So the slide I'm using is like some draft version of it. So there will be like some imperfections every now and then, but yeah, we'll do the best we could. Okay, so talking about the connections, these red arrows, well, so the existence, a possible existence of such arrows was you know, pointed out in the paper in 2018 with Sun-Mo Chun and Sergei Gufulkov and Sarah Harrison. And then we extended it and then sort of to turn sort of these example-based observations into some more systematic proofs in one paper earlier this month with the same team plus my student Davida Passaro and Boris Feiging. And in terms of quantum modular forms, that's work that hopefully will appear soon with Joanna Coleman-Lowy, who's currently a postdoc in Amsterdam, and my students. Okay, and I'll also refer to earlier works, and I'll give more reference as I go. Okay. So let's start with some sketch. I won't go into any detail, sketch of what this invariant is. Let's start with a physical picture. So we're considering M2 brane compactification on this background, and which is embedded in the 11-dimensional space-time that's given by a top knot in the time and some closed some tangent space is the closed free manifolds if you want. And then if we compactify it, on the 3 manifold, then what we obtain is a 3D supersymmetric quantum field theory. I'll call it TFN3. And we will, as advertised, we'll be looking at some form of supersymmetric partition function of this theory, which will turn into a topological invariant of the 3 manifolds. And in particular, since a cigar is not the compact space, we will need to specify some, boundary condition. And in the case of, the SU2 theory, well, we all know that there's an ADU version of this, and we'll talk about that later. But in terms of SU2, then these are in one-to-one correspondence, if you want, with the abelian flat connections on M3. So what's this supersymmetric partition function? Well, we will consider the Hilbert space that's vibrated by the U1 times U1 isometry of the top knots. And then we take an index like this. And of course, we can also consider it as a path integral with the appropriate things on it. And in particular, we see that because we have the cigar circle times this time circle, so the boundary is actually a torus, and we will denote tau as the complex structure of this torus, and Q, as usual, will be identified with e to the 2 pi I times tau. And since it's a counting function, we expect to get Q series with integral coefficients. So, right, so I'm just, this is just what I explained just now in terms of what everything is in this notation. Right, so heuristically, we can ask the following question. Since what we have is a 2D, 3D coupled system, and if we could, forget about the 3D bulk part for a second, we would expect to have some 2D CFT whose partition function should have some modular property. So the question is how much of that would remain in such a coupled system? Right, so if the bulk system, bulk theory is nothing, then of course we expect the result to be a modular form of some type. And if the bulk is, not too complicated, then we might expect, some sort of remaining modularity property. But in most general cases, we might, expect something to be whose modularity property would be so hidden that with the current technology, we can't recognize it, or, like mortals like myself. So we want to sort of work in the sweet spot. And another potentially useful point of view is that because of the, we can think about Z hat as some twisted partition function, and because of the twisting in the, in this interval direction, I mean, Z hat should be counting some, Q-bar cohomology of operators of the boundary theory. So that's yet another way to expect some remaining modularity at the hand wavy level. Okay, so we expect from this point of view some connection between these two circles. Right, and then now let's also expect, well, of course, I haven't told you what quantum modular forms are, but for now, it's just some generalization of modular forms. And there's also another way we can expect, we might expect one, you know, like Z hat invariant to have some sort of modular property. But before we go there, I might need to tell you first the mathematical definition of Z hat invariant, since the physical definition is for most M3 not very useful in terms of actually computing and obtain some Q series. So what is the mathematical definition? Well, first we need to restrict our level of ambition. And then let's just first focus on what's called the plot manifold. And the data that goes into such manifold is a plumbing graph, which is a weighted graph, which means that we associate each vertex some integer. Okay, so one example would be the cipher manifold with n exceptional fibers, and minimally, I mean, this n will just be the number of legs. I mean, so we have a star shape graph with just one center that has like n extended legs, and that would give you a cipher manifold. And inversely, all cipher manifold can be constructed in this way as a plot manifold. So, and I should say that the mathematical definition, I mean, I shouldn't speak for them since, you know, I didn't come up with it, but as far as I could tell, it's motivated by, first of all, the form of localization formula for simpler 3D n equals 2 theories, since in general, we don't really know what T of M3 should look like. And then the second thing is the expressions for the WRT Witten-Richteken invariants, Witten-Richteken derived invariants for such plot manifolds. Okay, and we will talk about the number 2 later. Right, so coming back to plot manifolds, oh yeah, so one thing to remember is that plot manifolds, includes all cipher manifolds, but many more. So coming back to the plumbing graph, okay. So another equivalent way to express the information contained in the plumbing graph is given by its adjacency matrix. So as the name suggests, it's an adjacency matrix, but I mean, we also put sort of these weights number, if you want, as the diagonal of such a matrix. And then what we actually do in order to get a plot manifold from this data is that we glue this bundle over S2 with the Euler characteristic given by these weights on the diagonals, and that will give you an 4 manifolds with boundary, and whose boundary would be the plot manifold, 3 manifold. And from this construction, you could already see that there are inequivalent graphs leading to inequivalent M4, but with the same M3. So, so these are called 3D Kirby moves, but I could guarantee you that the object we're studying, although its input is the plumbing graph, but the output is independent of such 3D Kirby moves. Okay, so this is the definition. So it's actually very simple. So with the plumbing matrix, I call it M, we define naturally a theta function, that you would naturally expect. And this B would correspond to the choice of boundary condition that we talked about earlier. So then Z hat invariant for these manifolds is defined by, you know, the contour integral of such a theta function and dressed up by these factors of z, and this factor to a power that's given by 2 minus the degree of the node. Remember, the degree of the node is the number of other nodes that it's connected to. So what am I doing with such a contour integral? Basically, I'm picking out the z constant terms. And if you want to think about it as some, you know, vector multiply and so on, we're then picking out sort of the gauge invariance operators, if you want. Okay, so one observation is that this theta function is only well defined if M, the plumbing matrix, or M inverse in particular, is negative definite. Right. Otherwise, you know, this is problematic, right? It would be a Q series, but also a Q inverse series, and we don't know where this function is defined. But after a closer look, we can see that the integral results in an infinite sum. So the integral is doing something interesting only for the vertices, the sort of, you know, the connecting vertices with degree at least 3. Otherwise, you know, this is just a finite polynomial in Z, and it just picks out 1 or 2 or 3 terms from this term. So there's no divergence that we have to worry about. So in fact, we only restrict, if we want to use this definition, we only restrict to plumbing matrix such that its inverse defines a negative definite space in the direction of these high connecting vertices with high degrees. Okay, so that's a technical point, although, you know, it will be important. And then this expression is for, you know, the A1. Oops. And you also see it being huge.
Yes.
Yeah. Okay, now everything's back to normal. Now this expression is for A1 of the ADE, and other AD groups can be treated analogously by basically replacing this matrix with a higher dimensional matrix. Okay, so as I mentioned, this Z-hat's invariant mathematical definition is written down to design in such a way that it's actually can be considered as a generalization of the WRT invariants. So recall that this is a Chern-Simons invariant, so it takes an integer as an input and it spits out the complex number. So this integer in particular is the, you know, the effective level of the Chern-Simons. So of course, it has been a very old question, like can we define, you know, an invariant on the, you know, continuous domain, for instance, the upper half plane instead of a discrete domain, and have an invariant that extends WRT. So an old idea, okay, is to have a Q series. And when you take the so-called radial limit, which is, you know, in terms of Q, it is really approaching the unit circle, the roots of unity, in particular, the case of roots of unity. And in terms of upper half plane, the tau plane, you're just approaching 1/k. When you take this limit, you recover the WRT invariant. So the work of Habira, for instance, is very much in this direction. But the difference is that recall that this constraint, the star equation doesn't really constrain fully the Q series, because you can always add an infinite Q series, like for instance, a cusp form that vanishes at all cusps. Then, you know, the Q series would be drastically different, but the star equation would still hold. So the approach of the z-hat invariant is that it's actually a definite Q series, as you could see from the mathematical definition. And moreover, it's proven for Plum manifold that it does recover WRT invariance if you do two things carefully. One thing is, as I said, the radial limit a la the old idea, and the other thing is you have to sum over the boundary condition appropriately. Okay, then you get WRT. So one property of the WRT invariance for Plum manifolds is that it has very nice trans-series expression in the semi-classical limit. Roughly speaking, it looks, pictorially like this. So WRT at level K is related to WRT invariance at level at tau equals -1/k. And this piece will correspond to the settle point contributions for the Chern-Simons, and then plus some perturbative series. So this is one way one might expect like something like a modularity property, because from this dictionary of identification between tau and k, and so this is nothing but the S transformation on the tau plane. So then the fact that the two differs, well, approximately speaking, with just a perturbative series is exactly, as we will talk about later, what quantum modularity is about. Namely, it's a modified modularity property at the radial limit. Okay, so we have this connection from quantum modular forms to topology, WRT invariance. So we have seen these two arrows. So then it's natural to expect that indeed z-hat invariant is generically some kind of quantum modular form, and this is the first arrow that's I'll be talking about. Please interrupt me anytime. So the second, if you want, so if you have questions. So then the natural conjecture is, well, vaguely put, the z-hat invariant for, arbitrary choice of AD gauge group is closely related to a quantum modular form of some kind. Okay, so to explain this, so first, what is quantum modular form? So again, roughly speaking, look, like the old version still has this typo, but let's ignore that. Roughly speaking, a quantum modular form is a function whose so-called cocycle. What is a cocycle? It's measuring the failure of modularity at the radial limit in some kind of nice function. And it's first defined by Zagier in 2010. And then afterwards, by now we have a different sort of various different versions of quantum modular forms, but that's more or less the spirit. So a bit in more details. So we're talking about a function on the upper half plane, and we know that it has a natural boundary, which is the rational numbers, and together with the point at infinity, we call it the cusp. And then it has a nice property that our favorite group SL2Z acts on it transitively, meaning arbitrary 2 points in this P1 of Q are related by SL2Z transformation. Okay, so to define what I mean by the cocycle, right? So so this is the modular transformation that we're familiar with. So gamma of tau is just this rational linear transformation of SL2Z, and W is the weight modular transformation. And then the cocycle is then defined that the difference between, its modular where here X is a rational number. So we'll be approaching it from within the upper half plane. Right. So in particular, if F is a modular form, then H in the right-hand side vanishes invariably. So the cocycle is always 0. So which is, of course, a very nice function. 0 is a very nice function.
Miranda?
Yeah.
How do you choose or determine the weight, the W?
Yeah. So indeed, so W is, if you want, a part of the definition. You say that the quantum modular form of weight W is a function. So it's if a function is a quantum modular form with this definition of the cocycle with a given weight W, then we call it a quantum modular form of weight W.
Mm-hmm. Okay.
Yeah. Sorry for the slightly imprecise way of talking about it here. So as I advertised, quantum modular form can be seen as a generalization of mock modular form, which is a generalization of modular form, and the most easy uniform are the theta functions. But it also contains other families that are not mock. So for instance, the full theta function, which I will define later. So to talk about the functions we involve that play a role here in Z hat, we have to define something else that's called the Eichler integrals. So let's consider a modular form of, like an actual modular form of weight W. And then we define two versions of integrals. One is a holomorphic Eichler integral. It's really an integral with some kind of measure factor. And then we integrate from tau to I infinity. And the non-holomorphic version, which depends both on tau and tau bar. Later, I'll view tau and tau bar as independent from each other. They are not necessarily complex conjugates. So one appears here in the range of integration, and the other in the sort of measure factor. And we could see that, these Eichler integrals viewed as a function of tau, they are quantum modular. One way to see it is we just compute its cocycle. And then as I here have done the computation here for you. Using the modularity of this function g, we could see that the cocycle is actually kind of a period integral of modular form here. So it is nice since it has all the analytic property if you want. For instance, if W is 3, for instance, then as a function of tau, it's just a polynomial of degree 1. Right, which is certainly nice in terms of, analytic properties. Right, so it has also a very nice property, namely, like if we look at the radial limit of the two versions of Eichler integrals, and then you can see that they're sort of continuous. They approach each other when you approach, for instance, here, drawn here is the rational number 0. Okay, so if two functions have this property, okay, let's formally put the asymptotic expansion near the point 0 is exactly matching from when one goes from the upper and the other goes from the lower upper half plane. So if two functions have this property, we call them the companion. And one, well, here, before I said that full theta function is a nice example of quantum modular form, and what is it actually? So let's consider this ordinary theta function of weight 3/2, which is just a theta function of a one-dimensional lattice, and of the norm given by 2am if you want. Okay, and then it's a nice, so you take this to be G, and its holomorphic Eichler integral would turn out to be this thing. So it's called a full theta function because apart from the plus or minus 1, then it is just a theta function. Okay, so it's a very simple function with the coefficients being plus 1 or minus 1. Okay, so a quick reminder why Mach modular forms fall into this category. A Mach modular form, let me remind you, is a holomorphic function such that there is a modular form G, which is called the shadow of the function f, such that if we compare, if we compose a new function, now depends both holomorphic and non-holomorphically on tau by putting f together with the non-holomorphic isolated integral of G, then f is like a modular form, and then we call the original function a Mach modular form. Okay, it's just a quick reminder of the definition. If it's too complicated, forget it. But and then one thing it's nice is that one can show from the definition of Mach modular form that the asymptotic expansion near the rational point actually looks the same as the G hat, as the G star. So if the Mach modular form is also a companion with G tilde, once you deal with potential infinities carefully. So of course, modular form is an example of Mach modular form. You just have to put G to be 0. And then other examples include the beautiful functions of Ramanujan. For instance, here, if you don't like it, don't look into it, but it's just some very nice function with all kinds of nice properties. That's called F0. Okay, so now let's go back to Z hat, the first example. Let's just take this plumbing graph, very simple, and then just plug it into the formula as the definition I showed you earlier. And then then the definition spits out an infinite Q series, and lo and behold, you can see that it's, a full theta function. It's a linear combination of full theta function. And which is, okay, fine. So in this case, you literally verified that Z hat in this case is a full theta function and hence a quantum modular form. And it also has the nice property that this specific combination of full theta function is indeed the isolated integral of the shadow of the F0, the Ramanujan's function that I just showed you. Okay, so, well, a nice example, but actually all this game starts with examples. That's how we started to look into this. And with some effort, you can prove general results with the mathematical definition as a starting point. So you focus on so-called negative cipher with 3 manifolds with 3 singular fibers. So the plumbing graph looks like this. And you can show that there exists a positive number such that Z hat up to some, finite polynomial, potentially enough up to some overall factor that's not important. It's just given by a linear combination of the full theta function of the same lattice. And you can change B, you can change the boundary condition, but as long as you stick with the same manifold, this lattice, underlying lattice, is the same. And then, okay, then you can, things start to get more interesting. You can look at more general negative cipher manifolds, which involves like adding more legs into your plumbing graph. Then you can show that sometimes it's no longer a quantum modular form on the nose, but it's a linear combination of all kinds of derivatives of quantum modular forms. So, so you could show that
Miranda, I think your internet froze. Okay, let's see. I'm sure she'll sign back in. Oh, there you are again.
Hi. Sorry,
Okay,
so I dropped out.
Yes, we missed sort of most of the last minute or so. I think you need to screen share again, please.
Ah, yes, that's a good point.
Yes, I think you we got this part about that they're not derivatives of the QMS.
Sorry?
In the more general case that there are derivatives, if they're not just three-legged but higher, more legs than
Yeah. Then you get, thank you. So I'll pick it up from there. Then you get a linear combination of derivatives of quantum modular forms, and you could go ahead and show that in such cases, well, for instance, the expected, the trans-series expression of WRT and all that is still intact. So, you learn something that's, you can generalize it and still having the desired property. But good, that's, So that's what we know. And then how about the so-called positive cipher manifolds? So namely, the plumbing matrix now is no longer giving you a well-defined theta function. But so in this case, we don't really have a mathematical definition for Z hat, but we do have some hints. For instance, if we flip the orientation, then we know of M3, we know that WRT invariants are just, related by flipping the sign of the effective level. So from the map of between K and tau, then we expect that in some way we're also flipping the sign of tau, which seems to be quite dangerous because, we're going from upper to the lower upper half plane. But anyways, using some number theory arguments, we can conjecture that if before flipping the sign, you get some full theta function, then after flipping the sign, you should get a mock theta function, which the shadow that's given by, what's being integrated in the Eichler integral. It's pretty wild if you, in fact, this relation because mock modular forms and full theta functions are completely different objects. Well, for one thing, like full theta functions, as we see, it has very small coefficients. In the examples we talked about, it has coefficients given by 0 or 1 or +1. And the mock modular form, mock theta functions, on the other hand, have like exponentially growing coefficients. So they are really different. But anyway, it seems to be working, and in this paper and some follow-ups we're working on, there will be a more systematic construction. But for now, it would be very nice to look at this example again. So this manifold, which is a Brice-Korn sphere, I showed you earlier the plumbing graph. We flip the orientation, then this manifold, if we flip the orientation, then this manifold can be constructed using some dense surgery of knot complements. And as I mentioned, Z hat is also defined for knot complement, which comes with some surgery formula. So using from that point of view, you can compute term by term what the Z hat should be. And we're very happy that lo and behold, it does give you the Ramanujan's mock theta function. So although sort of the mock modularity or quantum modularity is completely opaque in their construction. Okay, so we're just, we can keep on explore the relation between quantum modular forms and Z hat in other situations, since as I advertised, we want to establish and understand this connection as much as possible. So for that, let's push another frontier, which is to drop SU2 and consider sort of higher rank gauge groups. So for that, we need to introduce a nice concept of higher depth quantum modular form. And well, it's a it's defined recursively in the sense that quantum modular form of depth n is a function such that the cocycle itself is a sum of quantum modular forms of depth less than n. So it might seem a bit strange, this definition, but we have seen something like this showing up very naturally in the context of mathematics and mathematical physics. Namely, the indefinite theta function of like signature n, 1, when n is larger than 1, is in recent years, we have understood that it's a higher depth Mach modular form, which is a special case of a higher depth quantum modular form. Okay, this is all a little abstract, but very concretely, the role of Euler integral is not replaced by iterated version of that. So for instance, the double, recall that, we have, this is the non-holomorphic single Euler integral. And then in the case of depth 2 is replaced by the double Euler integral. Oh, D should be a G, I'm sorry. So as promised, we put, G star, the single integral in it, and with a new variable Z, and this Z will be, again, the variable of integration. So this thing is really a double integral if you write it out. Okay, so then what can be shown with some effort is that if we again look at the negative cipher manifold with 3 singular fibers, but now it's SU3 gauge group, well, one can show that this guy is a sum of depth 2 quantum modular form. And more interestingly, you can show a recursive relation between the quantum modularity. Namely, if the SU2, the A1 version has a companion that's given by G star, then the A2 version, the companion is in the span of, the double Euler integral involving this guy G prime, where G prime has to be in the SO2Z, in the modular orbit of the original thing. Okay, so these can be shown, and what is the general structure? The general structure is, well, this is just a conjecture, an extrapolation if you want, but it's hard to think, so that's the relevant depth of the quantum modular form in the general case will be R times K, where R is the rank, and K of the gauge group, and K is the number of nodes of the connecting nodes. For instance, in cipher, K is 1. And also a recursion relation should also hold in higher rank, if I may guess, that the companion would then involve the modular orbits. Here it's just G, and here for R larger than 1, then it should be larger than 2. It should be involving all companions of lower ranks. So you might have noticed that this is very reminiscent of the Waffle-Witten case of higher depth Mach modular form, so which is captured in this formula. So I think the reason is that the physical origin is the same, that you would have reducible, contributions from reducible connections involving. So that's sort of the picture here. Okay, so then we have seen the connection to quantum modular forms, and I would like to say something about the vertex operator algebra, how that comes about. Or is there a question that I could answer at this point? Okay, so so in terms of VOA, I mean, so well, the simplest family of logarithmic VOAs. Well, what does logarithmic mean? That means it's not a rational vertex algebra, and then also like we have modules that are sort of like a mess. Yeah, but so what is a mess? Like indecomposable, but they're not irreducible. Okay, so one simplest family of this is given by m, so which is a positive integer again, and then you can have some construction of a free boson, and then it comes with two types. I mean, the basic type is sort of the triplet algebra. You're just taking some kernel in a lattice VOA with this one-dimensional lattice. And the singlet algebra is its subalgebra. You're just sort of taking the zero charge part of that. Okay, and we're actually very familiar with some of this because when m is 2, then what we get is symplectic fermions, which are basically just the beta gamma systems. So now, well, we can look at characters, and so the singlet characters of the so-called atypical modules of these algebras. The singlet characters are basically just can be obtained by taking the z constant terms of the triplet characters, since you know the construction of the algebra is given in such a way. And what's interesting is that you could immediately see that you know, for the 1,n singlet algebra, then up to some factors of eta function, the characters are again given by full theta functions. So the characters are monomodular forms. So so we see that these two boxes are kind of related together via characters. Okay, then how do we understand quantum modularity from this point of view? That's an interesting question, and I don't think I can give you the full answer. I think there is a lot to be understood there. So first, well, the failure of modularity, why is it no longer modular? We know that it's because the theory is not rational. So, or the Drew theorem, etc., just doesn't apply. However, it has still some nice features. For instance, you know, from similar consideration as the Chern-Simons trans series expression, we can also convince ourselves that some version of Cardi-like formula could still, you know, be written down. So it's wild, but it has still some nice things to it. And that's maybe also what we expect, since log VOAs are really nice for compared to generic irrational theories. Okay, so we have this arrow between z-hats, invariants, and quantum modular forms, and we have this arrow, so we should immediately have part of this arrow is relating z-hat invariant to VOA characters. Yeah, so for instance, I mean, we already have this result on full theta functions in the case of, you know, grouping SU2 and then, you know, this very simple cipher manifold. And we can just translate that and to say that z hat is up to some factors of beta function, the character of some singlet algebra, which is very cool. But can we understand things a bit more? Yeah, so maybe it's illuminating to understand that it's maybe not such surprising. We also, you know, quite, you know, it's not also not surprising from the point of view of like we're computing some partition function of a 2D, 3D coupled system. So just one simple, you know, example, we can take this field content, this 3D theory, and with the accompanying boundary condition, and we start to compute the corresponding index. And when we do this integral, indeed, what we get is, a full theta function up to a eta function, which is the character of the symplectic fermion, which is one of the 1, m families. Right, so of course you can say more words about it, right? Like this VOA must be, the algebra of, local, the BPS operators on the boundary and so on and so forth. But the truth is that, we don't know the generic 3D theory, so understanding, so getting to know the VOA actually, hopefully will give us some information. The connection might be makes more sense in that way. Okay, so in a bit of remaining time, well, I started a little bit later, right? But I also don't want to take too much of your time. So we can just also establish directly the relation between VOA characters and z-hat invariants. Not just by, combining these different arrows, just look at them directly. So in fact, this 1, m algebra is for the special case that of the SU2 case again. And about 10 years ago, Fagi and Tipuni has constructed, the similar and the analogous algebra for corresponding to arbitrary Lie algebra. So we have such, algebras constructed, and we have their characters. And note that these characters are known to be depth R. R is the rank quantum modular forms only for a very low line case. And thanks to the very recent work by this group. But actually, we can prove a bit more. We can prove that, again, using this, in the case of this very special 3 manifold, the cipher manifolds, we can prove the connection to arbitrary gauge group. Okay, so that's not a big deal. It just, you just have to show it. And actually, it's quite interesting because the connection, also already happens at the level of the integrand of z-hat. So that probably says something about the field content before you, gauge the U1 symmetry or whatnot, or the gauge symmetry in general. Okay, so we can also, do a bit more general 3 manifolds, again, cipher manifold. And if you have 4 legs, then what you get is no longer 1, m log VOA, but another type of log VOA, which is called the PP prime, given by 2 integers, and as the name suggests, is an extension of the minimal model. So we know that there's no 1, p minimal model is trivial, but there is still a log VOA. And then similarly, actually, the way you extend the minimal model to the log model is similar. It's just, in one case, if p equals 1, you actually get a trivial theory on one side. But in any case, we can show that they correspond to this type of 3 manifolds. And I should also say that there are not so many log VOAs constructed. So we're sort of just, you have to, get a bit inspired. And of course, the hope is that we will find a way to construct VOAs from 3 manifolds one day, but that day hasn't come. So so far we've been only working with known VOAs. And also you can think about including Wilson line operators in your partition function. And interestingly, that leads to other modules in the same VOA. So that also makes sense. You're not changing the boundary algebra, if you want to use these words, but you're accessing other modules of it. So what we have seen here is, okay, in the first part, we have seen that we can understand sort of the quantum modularity properties of Z hat in various points of view, although the details is quite complicated and there's still, unexpected features. And then similarly for VOAs, I mean, yeah, so you can go through quantum module forms, but in fact, there's a more direct relation to the rest of the story. And one thing that's missing, one thing, well, not really missing, but I haven't had a chance to talk about is how VOA is related to, this box of 3 manifold topology and knots. And I can just say that, for instance, there's very interesting things to be learned there. For instance, using the knot quiver correspondence, we have a different way of expressing the same Z hat, using some num sums, and then that leads to very, new expressions for VOA characters that are not obviously not obvious at all from the VOA representation point of view. And also, when this num sums will give you quantum module forms, that's also kind of an open problem. So, well, I had written an open question slide, but I think I lost that version since I only had the draft version. So there's will not be the open question slide. So this is the final slide, but I can tell you, like, yeah, obviously there's a lot of open questions, and each arrow, it has more to be understood and can lead to more applications and insights. So if my own sort of using the last minute, my own wish list would be a more systematic understanding, since I like, number theory, to the relation between the mock, the Z hat for the flipped orientation, or why the functions behave so wildly different. Of course, we know that M5 brain theory is not, it's Cairo, but I would like to understand a bit more. And similarly, I mean, we have some construction identification, at least construction might be too big a word, of the VOA corresponding to M3, and how about, a systematic treatment of the VOA of the flipped manifolds. We know that the character, if everything works well, then the character should be given by Mach theta functions, and there are VOAs on the market which do that, but not doing that in a very systematic way. So hopefully Z hat can actually help us to do this. And then there's a lot more, and of course, the end of the day, I would like to understand a bit more of the 3D theory. And before that, just a more systematic construction of M3 of the VOA corresponding to arbitrary closed 3 manifolds, maybe, that's compatible with gluing, and that kind of operations will be very delightful. And with that, thank you for the attention.
Well, thanks very much, Miranda, for this really nice talk. Other questions? So maybe I'll start. So could you add a little bit more explanation how we should think of this VOA connected to M3? Is there sort of a direct, so more physical understanding of where this log CFT should be coming from, or this log VOA?
Yeah, so I mean, since Z hat should be enumerating the Q-bar cohomology of boundary operators, then the logical words to say here is that these VOAs are an algebra of these boundary operators. and that's the expectation. And as I showed you in this very simple example, we could sort of see how this log VOA characters get, come about in that very simple 3D theory. But yeah, I'm not sure I can have something more concrete to say at this point. But obviously that's one of the most interesting questions.
Okay, do we have any other questions? You can just unmute yourself and start asking away.
Hi, Miranda. I see you have the not quiver correspondence there. I didn't quite get if you have, for example, optimistically, perhaps you can explain it, or I mean, I didn't quite get how your story connects to it.
Hello?
I think, Miranda, your internet slightly froze. Alessandro,
Yeah.
repeat your question.
Yeah, for a while, I didn't hear or see anything.
I see. So, well, I'll try again. Perhaps I'll say that.
Oh. Hi, Alessandro.
Hi, Miranda. So I was wondering how your story connects to the not quiver correspondence, since you mentioned it there. I didn't quite get if you have, if you have anything to say here, or if you just would like to.
Well, actually, yeah, concretely, I mean, not quiver correspondence gives also a recipe to write down z hats, and then for not complements. And then you use the Dan surgery formula, then you can also, view the same three manifold, not as a plumb manifold, but as some result of a Dan surgery of some not complement. Then you get two expressions for z hat that looks very different.
Wait, one is from the not complement, and to the quiver, what do you associate?
For quiver, you basically associate some quiver, some matrix, and then that will give you another, lattice, and then you have some denominator, and you get a num-sum like formula. And then from the point of view of plumb manifolds, as I showed you, you're just doing some silly, contour integral of some dressed up theta function. And the theta function, that lattice is not the same lattice as in the num-sum, it's the lattice of the plumbing matrix. So on one side, it's more obvious that you get some, some quantum module form like full theta function and so on. On the other side, it's like complicated cancellation and all that, and you get the same results. So then you might wonder, like, for instance, how maybe I should have known from the look of this num-sum that it should be a quantum modular form, but I don't know. So how, or should this thing, and since this thing is a VOA character after all, then, maybe this num-sum has also some VOA explanation or such things. And I think these are pretty fun questions. Does that answer your question?
Yeah. Well, it's more than I hoped for, actually.
Okay, there was a question whether the slides can be shared, the annotated ones. So if you can actually email them to me, please, Miranda, and then I can upload them to the web page. Are there any other questions for Miranda? I actually am aware that it is now 1:08 where you are, so we might not want to keep you for too long, but.
No, I mean, I can answer questions, or I can also go to sleep if there's no questions. It's all fine.
Okay, I don't see any immediate questions. Maybe we
Okay.
can switch off the recording, Jonathan,